Hello and welcome to another STEP video. This time I'm going to do question 2 from Step 2 2021. So I'm just going through the Step 2 2021 paper at the moment. I'll probably be going through the Mat 2012 big questions as well soon as well. So sorry if I'm kind of muddling these up, but I'm trying to help those students who are doing Mat, but also some who might be thinking about doing the STEP as well. I don't mind doing some Tamura papers as well actually, because I know that's getting increasingly more popular. I'm very happy to do that. And I think the Advanced Extension Award still exists, but yeah, it doesn't seem so popular anymore. Anyway, let's actually have a look at this question. They're all the same, honestly, like any of these tough questions, extension papers, whether they're from the Olympiad or any of these papers. You know, it's just interesting maths questions, so let's do it. My intention is very much not to say, you know, that like you need to be brilliant to get these right, because I don't think that's true. You need to do lots of practice, sure, you need to do lots of practice. Nobody's successful in these exams unless they've practiced loads. But you don't have to be, you just need to have seen a lot of the tricks. That's what I think with a lot of these questions. Okay, this question, not too bad, I think. Let's jump into it. Okay, they warn us straight away. A, B and C may be complex numbers. Ooh. That sounds interesting, and it's interesting to me actually, because Step 2 I always thought was it claimed to be only A-level maths. Well, if A, B and C can be complex, it's definitely not only A-level maths, is it? But there we go, you know, like clearly Step 3 is definitely focused on further maths topics and Step 2 is focused on A-level topics. However, the fact that they're saying A, B and C may be complex there means you really should have seen complex numbers before, at least when you do this, so there we go. Okay, so let's not worry too much about that. First, they've just said initially P, Q and R are real numbers. Okay, so they're not complex. P, Q and R are real numbers. And given that there are numbers A and B that satisfy A plus B is P, A squared plus B squared is Q, and A cubed plus B cubed is R, then this must be true. Okay, right, let's do it. So I'm going to jump into this. I guess my first thought was, well, if I take this and square it, I get something like that. So if A plus B is P, then A plus B squared is P squared, and clearly that's A squared plus 2AB plus B squared is P squared, but A squared plus B squared is Q, so you've got Q plus 2AB is P squared. Okay, that's kind of interesting. That feels like we've got somewhere. We might as well you know, kind of like rearrange these a little bit, but not before we've kind of thought, well, probably best to try a similar trick with this, but to introduce R. So this time I'm going to cube it. So this is all really going from the first one. A plus B all cubed is going to be P cubed. Ooh, my handwriting is deteriorating again. And so that's going to give us A cubed plus 3a squared b plus 3ab squared plus b cubed. Let's move over. It's p cubed. But a cubed plus b cubed is r, and then you can factorise out the 3ab, leaving a plus b, and that equals p cubed. Well, a plus b we already know is q. And AB, I can actually rearrange this to make this AB equals P squared minus Q over 2. And so that's going to be 3 times by P squared minus Q over 2 times by A plus B, which is just P, equals P cubed. I'm trying to make this clear for you all. Okay, so I reckon we're really close to this now. We want it as 3pq minus p cubed is 2r. Well, let's double everything. And I suppose multiply that out to 3p cubed minus 3pq equals 2p cubed. I think I've doubled everything there. And I think the result I'm trying to prove is just here actually. It's basically there now, because 2r is going to be 3pq minus p cubed. Is that what I was trying to show? Yeah, 3pq minus p cubed is 2r. Brilliant, so we've got it. Now, the second part of the question is where they get you to do it in the other direction. This is about implication. If A then B, and if B then A. So this time we're not going to be told that these three equations are true. We're going to be told that this last equation is true. So we're given that 3pq minus p cubed equals 2r. We're given that pq and r, the real numbers pq and r, satisfy that equation. So I'm going to write that down. Given that 3pq minus p cubed equals 2r, yeah, we're given that, and then we're told to deduce, essentially star, we're supposed to show that there exist numbers a and b such that those equations hold. But it does give us a hint. It says by considering the equation 2x squared minus 2px. So I'm just going to put here prove star, and I'm going to say consider, because it's giving me a hint about how to do this, consider 2x squared minus 2px plus p squared minus q equals 0. Yeah? Well, what can we say about this? Well, there's a lot we can say about it. We can talk about the sum and the product of the roots. Now, you want to be aware of sum and product of the roots. It's a topic in further maths, but I think it's in the very first book, so it's not too bad. But what we have is minus b over a, which would be 2b over 2, is going to be the sum of the roots, yeah? So let me just say, consider this, and let's say it has roots alpha plus beta. Sorry if I sound, oh sorry, alpha and beta. And sorry if I sound slightly put off. I can hear my son hammering at the door of the shed trying to get in. Anyway, straight away we can see that P is alpha plus beta, and actually alpha and beta are going to turn out to be A and B. That's what's quite nice about this. We can also say that the product of the roots, which is alpha beta, is going to be, we've got minus b over 8 c over 8, so p squared minus q over 2 is going to equal alpha beta. And if you remember from the last part, that's exactly what we had. Apologies if you can hear my son screaming in the background. He just wants to come in the shed. It's not that he's locked in a shed, it's that he's locked out of the shed where he belongs, outside of my shed. Anyway, so we've got kind of like some of these results, which is kind of nice. Now this actually leads directly to q equals a squared plus b squared if you combine it with this, because obviously we can then say thus p squared is going to be alpha squared plus 2 alpha beta plus beta squared, but of course if we plug that in there we're going to get p squared equals alpha squared plus 2 times by this, well that's p squared minus q, and then plus beta squared. In other words, what we're going to get is q equals alpha squared plus beta squared. So we've already shown here directly from this that the star holds provided alpha equals a and beta equals b for the first two equations. Yeah. All I need to do now is use my given result. Apologies, there's a plane going overhead. I don't know if you can hear that. Everything's conspiring against us for me to explain this, but all I need to do is now use this last result to show that r equals a cubed plus b cubed, and that's what I'm going to do. So, using the fact that 3p cubed minus p cubed equals 2r, we can say, well, 3pq is, let's have a look, what's 3pq here? Well, p is alpha plus beta, q is alpha squared plus beta squared, and then we've got p cubed, which is alpha plus beta cubed, equals 2r. And just multiplying this out and simplifying it, it does very much feel like we're just doing what we did in the first part, but backwards. We get 3 alpha cubed plus alpha squared beta, I'm just doing that one times that one, that one times that one, plus alpha beta squared plus beta cubed minus alpha cubed minus 3 alpha, plus 3 alpha squared beta plus 3 alpha beta squared plus beta cubed. Well, that's going to equal 2r. And now what happens here? Well, your 3 alpha cubed minus alpha cubed becomes 2 alpha cubed. Your 3 alpha squared beta and your 3 alpha squared beta there cancel. Same with the alpha beta squared and the alpha beta squared. but then you've got 3 beta cubed minus a beta cubed, which is 2 beta cubed, and that equals 2r, and hence alpha cubed plus beta cubed equals r. Okay, so what have we shown here? So given, it's sort of like write a concluding remark, so given 3pq minus p cubed equals 2r, yeah, it's certainly the case, it follows that there exists, that's a there exists symbol, numbers a and b, which in our case are alpha and beta, yeah, such that a plus b is p, a squared plus b squared is q, and a cubed plus b cubed is r, yeah. So there we go. Now you might say, well, you know, I just want to explain the trick they've done there. Basically, you know, they've come up with a quadratic, yeah, and they've just shown with that quadratic, you know, obviously these numbers are the roots of that quadratic, so they must exist, yeah, because the roots of a quadratic, of course, they can be, you know, they can be complex, that's absolutely fine, but yeah, the roots of this quadratic must exist, and therefore, like, you know, we've got the values that we need. I hope that settles that question. But it's a clever trick. They're just saying by considering that equation, so that there exist numbers a and b. Because remember, a and b can be complex. It's not a problem at all. And the roots of quadratic can be complex. So we can certainly use this quadratic to demonstrate it. Okay, so that was part 2. And I didn't mind part 1 or part 2 here. And I didn't mind part 3. In fact, I actually would say I really like this question. I preferred it to question 1. The heavy trig ones always can just confuse, I think, and baffle. And they're very long on how much you've got to write down. They really are. And this one's quite algebra heavy, actually. I don't think this is algebra light by any means. Okay, right. It says show using part 1 that if this is true, and once again, S2, U and V are real numbers, but A, B and C could be complex. Yeah. Now they're distinct numbers A, B and C, such that that's true. And we've got an extra one here, which is like the product of the roots. Now we're going to show using part 1 that C is a root of that equation. Now if I'm using part 1, then the first thing I'm going to do is change these statements by moving the C over to the right hand side. So I'm going to have A plus B is S minus C. A squared plus B squared is T minus S C squared. And A cubed plus B cubed is U minus C cubed. Cool. And let's not forget that ABC equals B. But that's what I'm going to use first, because then I can just sort of jump straight into the question and say from part 1. Now, what did we know from part 1? They said that given this was the case, that we knew, given that was the case, that we knew that this is true. What we showed that. So I'm just going to plug it into now 3pq minus p cubed equals 2r. I think that's the statement. Let me just write it down again so I can see it. 3pq minus p cubed is 2r. So I'm just going to use that, but remembering that p is a plus b here. Now p has become s minus c. This is like your p, this is like your q, and this is like your r, isn't it? So now I'm just going to replace. So from part 1 we can deduce that we've got 3 times s minus c times by q, which is t minus c squared, yeah? Now remember, what are we trying to end up with here? Because I'm always thinking, does it look like what I'm supposed to end up with? We're supposed to show that c is a root of this equation. Now if we get this equation with c replaced with x, then c is definitely a root of that equation. So that's what I'm hoping for here, because I'm going to come up with an equation with lots of s's, t's and u's and c's in it. Well, that's exactly what this equation is, but with x replaced with c, and that will show that x is the root. So I'm just going to plug it in. So 3pq minus p cubed, well, that's going to be s minus c cubed, and it equals 2 times r, well, that's 2 times u minus c cubed. After that, it's just an exercise in a lot of algebra, really, because we're going to have 3 times by st minus ct minus sc squared plus c cubed minus this old chestnut again, s cubed minus plus 3 s squared c plus 3 sc squared plus c cubed. Try and be as neat as you can, or you start making mistakes in your own handwriting here. And that equals 2u minus 2c cubed. Now this is where I'm actually going to do something here. Can I just quickly, because I hate working without being able to see directly in front of me the result I am trying to prove. So I'm just going to actually take a little screenshot of that result and copy and paste it so it's right next to where I'm working. Okay, that should have done the trick. Right, so here's what I've got. Let's just put it in the corner of the screen, what I'm supposed to end up with here. So there we go. You'll see that. Hopefully you can see that. Brilliant. Right, it just makes things so much easier. Now what do I get here? I get a 3c cubed, and then I'm going to get minus a c cubed, which makes 2c cubed. Slightly disappointing. Oh, but I've got a plus 2c cubed over here. So I think I'm going to get 4c cubed there. Let's have a look at this. Oh, hang on a second. This is, yeah, I've just realised some sign errors I've made. Look at this, s minus c all cubed. That's going to be a minus there, a plus there, and a minus there. And I noticed that because I started to realise, oh, hang on, I'm not going to get the answer up here, which I need. So always, you know, bear in mind that that's the other thing about looking where you're going. It will show you little careless errors you've made. I find I make a lot more as I'm talking through a question like this, because I'm kind of doing two things at once. I do make mistakes. I do definitely make mistakes, but I make more when I'm describing them in these videos. You may not believe me, and fair enough. Never believe anything I say. But after I've put all of the c cubes together, I'm going to get a 6c cubed here, yeah? And so that's kind of corresponding to this. Now they've got 6sc squared, because x is c in this really. Now, have I got that? sc squared, well, I've got a minus 3sc squared here. And then I've got another minus 3sc squared, so that's minus 6sc squared. There's no other sc squareds there, so I've kind of dealt with that one. Now, what about this? This is 3s squared c. And do I get a 3s squared c? That's from this one. Yeah. And then I also want a 3tc. Do I have a 3ct here? Yeah, that's that one. Try and be nice and careful. That's all of that dealt with. And then I've got a 3st. I've got a 3st there. And then I've got a minus s cubed, and that's this one here. All of these have been ticked now, that's why I do the ticking method. So I've done that, and then I've just got to take the 2u over, yeah? And so what I've done is I've multiplied it out, and I've shown that this is the result. If I can just comment it like this is the result I'm trying to prove. This is the cubic, but with c replaced with x. Hence, we can say that c is a root of that equation. Did they score it? No, I was hoping. Hence, c is a root of the given equation. Let's just put it like that. I do like to explain myself sometimes, and I think the examiner will like it as well. It just shows a little bit of like a consideration for the person marking your work. They need to understand what you're saying. Yeah? It's no good. You can't expect them to go, you know, do their very best to give you as big a mark as as possible, because they don't care about you. They don't even know who you are. Yeah. So try and at least make your working easy to understand, and they will, in return, I think, give you more marks. Okay, and write down the other two roots. Yeah. Well, look at this. Surely there's some beautiful symmetry going on here. Yeah. If C is a root, well, what's the difference between A, B, and C here? Nothing. There is a lovely symmetric relationship between A, B, and C. So if C is a root, then A is a root and B is a root. And we don't have to explain that. It just says write down the other two roots. It's obvious by symmetry that A and B are also going to be roots as well. So I'm just going to put A and B are also roots by symmetry. But you don't need the word by symmetry, but I'm just trying to explain to you. why it's true. A and B are also roots by symmetry. Look up symmetric functions and stuff like that. It's really useful for a lot of these extension papers. Deduce that s cubed minus 3st plus 2u equals 6v. Well, we haven't used this one yet, have we? So let's try using it. So ABC equals v. And as we've got ABC equals v, we should also note that minus d over a, and this is where we're going to come to the product of the roots of a cubic, yeah? Product of the roots of a cubic. If a cubic has roots alpha, beta, gamma, then alpha, beta, gamma equals, now minus b over a is the sum of the roots, c over a is a sum of the product pairs, and minus d over a, yeah, and I'm going to put that in inverted commas, is going to be the product of the roots, and that's for a cubic which is of the form ax cubed plus bx squared plus cx plus d equals 0, yeah, and that's exactly what we've essentially got here. If I can just look at this again, and minus d over a, so if I can just put it like this, now I'm trying to prove, I can't remember exactly what I'm trying to prove here, something in terms of S, T, U and V. So I want to keep the V and point out that minus D over A, that's going to be that last three terms there because they are terms independent of X. If I make that negative, so I get 2U plus S cubed minus 3ST over A, which is 6, equals the product of the roots. Well, A, B and C are all roots, so this should equal V, and then I think the answer pops out straight away. You get 2U plus S cubed minus 3ST equals 6V. Is that what they were looking for? S cubed minus 3ST, yeah, that's it. And there we go, we've deduced it. So we've just got part 4 to go. Okay, right, so it's looking good on this. I really did like this question. I think everything just kind of clicked with me when I was looking at it. It's not always like that in STEP, is it? But, you know, if you get lucky, you get a question where it's like, this is making a lot of sense. Okay, find numbers A, B, and C such that this is true. Yeah, we just got to find numbers so that that's true. Yeah, and verify that your solution satisfies the 4 equations. Well, if we look at this, A plus B plus C, we can start, you know, saying, well, that should be our S, and that should be our, that's the way I did it. I just simply wrote down this. So S is 3, T is 1, U is minus 3, and V is 2. It just seemed natural to state that, and then I plugged it back in to my equation up here, yeah, to see what cubic I got. I got 6x cubed minus 18x squared plus, okay, 9 minus 1, which is 8, times by 3 is 24x, plus, okay, let's do this carefully, 9 minus 27, that's minus 18, plus 6 is going to be minus 12, probably minus 12 equals 0. So that's just by plugging in those values into our cubic up here. Oh look, it's all divisible by 6. X cubed minus 3, let's get this right, 3x squared plus 8x. Divide it all back carefully by 6. By 6. I think I made a mistake when I originally did this as well, and I was sitting there for about 2 or 3 minutes thinking, why is it not factorising? Why doesn't it have any nice factors? Check you haven't made a mistake. Ah, yes, you have. Okay, because, you know, it's bound to have one nice factor, just like in question 1, factor theorem's your friend here. They love giving you cubics where it's up to you to handle it. Now look at this, 1 minus 3 is minus 2, plus 4 is 2, minus 2 is 0. So by inspection, x minus 1 is a factor, because we're just trying to find numbers A, B, and C, which, you know, which solve this. So this will be, you know, or which hold in this equation. Now remember, A, B, and C are the roots to this cubic. That's the point we were making in part 3. A, B, and C are the roots to this cubic. So lovely. All we've got to do is just find the roots to this cubic. So by inspection, I'm just going to go, okay, that needs an x squared to make the x cubed. It gives me a minus x squared, but I want minus 3x squared, so that needs to be minus 2x. That gives me another minus 2x squared. It gives me plus 2x, but I want plus 4x, so I need a plus 2 here on the end, and that gives me minus 2 on the end. However you do the division there, but please don't spend ages doing long division. It's, you know, just divide it. Okay, so we got x equals 1, or, now this is interesting, they said at the start a, b and c could be complex, so this is bound to have complex roots. If we solve it by completing the square, we get minus 1 plus 2, which is plus 1, and so x equals minus 1 square rooted, which is I, so you got 1 plus or minus I. Yeah, you want to be quick with those once again. Now it did say, it said find the numbers a, b and c. Those are the numbers a, b and c. We can have a is 1, b is 1 plus I, and c is 1 minus I. That's absolutely fine. But it did say verify that your solution satisfies the 4 equations. So we better check it satisfies the 4 equations, because look, the equations are right there. They're sitting in here like, okay, a plus b plus c is 3. Clearly the i's cancel there, and so a plus b plus c equals 3 is good. Yeah, what about a squared plus b squared plus c squared is 1? Well, we'd have 1 plus, now 1 plus I squared is going to give you 1, 1 squared plus I squared. I squared is minus 1, so the 1's are going to cancel. And you're going to be left with then 2i. Similarly, you're going to have 1 plus I squared, which cancels, but you're going to get minus 2i. And that does equal 1. So a squared plus b squared plus c squared works, yeah? You need to be able to do this without a calculator, remember. So put the calculator down. You know, lose your attachment to the classwords. Okay, the one annoying one, I suppose, is a cubed, b cubed, c cubed. Well, a cubed is 1. B cubed is going to be, well, b squared, if you remember, was 2i. So it's going to be that times by b, and b is 1 plus I. And so we end up with 2i plus 2i squared. Well, that's just minus 2. Yeah? C cubed is going to be similar. It's going to be minus 2i times by 1 minus I. And that's going to be minus 2i plus 2i squared, which is minus 2. And so a cubed plus b cubed plus c cubed, well, it's going to be 1 plus 2i minus 2 minus 2i minus 2. And so that comes to minus 3. Is that right? Yes, it is. I've just looked up and seen minus 3. So look at this. They're all working. Last one, times them all together. And if you do that times that times that, well, 1 plus I times 1 minus I is going to be difference of 2 squares. It's going to be 1 squared minus I squared, which is 2. And hence, after you times it by 1 as well, you get 2. So all 3 equations work, and you know you've got the question right. Well done, you. Well done. Okay, that concludes this video. Hope you found it useful, and let me know in the comments if you've got much better ways of doing things. I'm always interested to hear those. Okay, bye-bye.